We have Brian Pales from Vector Corrosion Technologies.
On the program, I said Chris Ball would be presenting. Brian Pales, we actually switched presentations, so this afternoon when it says I'm presenting, he's actually presenting. So sorry if you expected Chris. I hope I'll keep up to his level. So today we'll be talking about evaluation methods for the preservation of bridge decks. One of the biggest preservation challenges with bridge decks is corrosion, specifically de-icing chemicals. Not so much here in Florida, but obviously our northern states, western states use a lot of de-icing chemicals due to freezing. These de-icing chemicals get into the concrete and cause corrosion. So just a quick little background on what exactly is the corrosion reaction and how it affects our reinforced concrete structures. Here is an example of a corrosion cell. We have 4 components. We have the rust, which is what we call the anode, where iron loses that electron, becomes iron oxide. That's the red rust that we're all familiar with. But there's 3 other really important keys to it. When we lose that electron, it's got to be a balanced reaction, so it has to get consumed over here at the cathode, which, you know, the big thing to identify is the anode's where section loss is, the cathode is not. And then we have to have some ionic current through the concrete, which is our electrolyte, and then we have an electronic path for that electron, which is the rebar. And what really causes our damage and our serviceability issues in reinforced concrete corrosion is the relative size of iron oxide. So as iron becomes iron oxide, it actually increases its relative size, and it can be 7, 8 times the size. So if you have an expansive product inside reinforced concrete, concrete is poor in tension, we start getting cracking, delamination, and obviously eventually spalling. So here we have the anode, and you can see the nice clean bar here. That is actually your cathode. So you can see the whole corrosion cells occurring right there. So how do we find deterioration in reinforced concrete bridge decks? Well, obviously visual inspection is extremely important, but it's important to understand that visual inspection is telling us what is the damage today. We can also do coring, which is a localized assessment of the concrete materials. We take one core, we know about that location. But we can also use non-destructive methods to kind of get a more global assessment of the deck and identify deterioration that may not be visible. So what is potentially the future condition of the structure? And kind of using these 3 methods together, we can understand what is currently the problem and where the problem is going to go in the future. You know, coring is obviously extremely important. Typically in bridge deck evaluations, we're looking at kind of 4 primary things. We want to know compressive strength, chloride concentration, how deep potential carbonation is, which is another factor for corrosion activity, and petrographic analysis. Is there any kind of chemical deterioration occurring? So chloride concentration, typically we're taking cores through the depth of a structure, a bridge deck, and in half-inch increments looking at the profile of the chloride concentration with depth. Here we have in chloride concentration in parts per million and the depth of the sample. And we want to see, you know, here we have some nice diffusion curves where we have high surface concentrations due to de-icing chemical application. Those de-icing chemicals diffuse into the concrete. Here we have more flatter curves, and those are kind of a typical of where you have cracking or a construction joint, so that diffusion of chloride occurs much faster. Generally speaking, 350 parts per million is about the threshold for chloride activation. This is not a hard and fast rule. It can vary depending on various factors. You can see I put the red line at 350 here, but at that concentration, the risk for corrosion activity is high. At the depth of steel, sorry. So it's important that that chloride content must get to the steel depth. When looking at decks, also, not only is the deck important, but how the deck has an effect on the substructure as well, especially with chlorides, specifically deck joints. We all have deck joint problems in every state, and they allow runoff onto the piers. Here, you know, I have a really good example. These are 2 different piers from the same bridge, reinforced concrete with masonry clad, and they're very different obvious visual conditions. One is clearly water stained, corrosion, and another one's in a pristine condition. The only difference between these 2 elements is this one has a continuous deck over top, and this has an expansion joint. And so the deck joints not only have an effect on the deck, but also the substructure below it. And you can see here's a chloride profile from this element where there's effectively no chlorides in the element at all. And then these are chlorides from this element, and you can see that well above threshold. So when we're looking at decks, we also are relating that also to the substructure as well. Carbonation is something that we don't typically, chlorides cause the problem first in a deck, but carbonation is an issue to keep track of, especially at cracking. Carbon dioxide can permeate into the concrete and react with the free lime, lowering the pH of concrete. When you lower the pH of concrete, the passivity of steel is broken down and you can start corrosion. Specifically, if we look, and I'll not favor one side, I guess. I don't know. It doesn't really matter. But as you see, here's a pH indicator solution on a core. The purple pink is where the pH is high, and you can see a crack where it's clear, and that's where the pH is dropped. So any kind of cracking or joints in the concrete can allow carbonation to reduce the pH around the concrete and around the steel and cause corrosion. We often see this when concrete permeability is high, industrial sites, or very old structures. Another coring technology that we use on decks, looking at petrography, identify the chemical characteristics of the core. What's the air concentration? Is there supplemental cementitious materials? Are there reactive aggregates, particularly ASR susceptibility? Here is an image of 2 reactive aggregates, and you can see the ASR gel forming around the aggregate. ASR gel is expansive, causes microcracking, it leads to cracking. And then cracking will lead to chlorides and carbonation getting into the concrete and cause corrosion. So, and here's a core. This is actually freeze-thaw damage, and it's a little hard to see, but all the little red arrows are pointing to microcracking. So this core didn't have any air, this concrete didn't have any air entrainment, so now it's causing freeze-thaw damage, microcracking, which is leading to corrosion. Here, this is a bridge. This is an older bridge. It's P Street. This bridge had no air entrainment, so it started to have freeze-thaw damage. You can see a core collected from the deck, just the subparallel cracking through the core. And that subsequently allowed a tremendous amount of chlorides and moisture to get into the rebar. And subsequent, you can see that the stirrups are completely gone. And then this is actually such an old structure. It has a twisted rod bar, which is not used today, obviously. But you can see excessive corrosion activity. Now, the corrosion didn't lead to the cracking led to the corrosion. So understanding cores and how they affect the bridge deck condition is extremely important. Those are that's a destructive methods. What are some of the non-destructive methods that we use to evaluate bridges, especially bridge decks? Well, visual inspection is a form of non-destructive testing. Chaindrag, ground penetrating radar, corrosion potentials, and impact echo pulse velocity. These are the things I'm going to kind of discuss in today's talk. One thing to kind of keep in mind is different technologies identify different deterioration states and are more useful at different stages in a bridge's service life. Here we have kind of a generalization of bridge deterioration, deck deterioration. We start at time 0, and then slowly deterioration is exponential. And we kind of indicate what different methods are effective at identifying different deterioration. Obviously, on a bridge deck, we start with chloride and moisture penetration. Then we have rebar corrosion. That leads to delamination and then eventually spalling. Visual inspection is really only going to identify where the spalls and cracks are. Chaindrag is identifying those late-stage delaminations. And then you can use some more effective non-destructive testing methods to identify earlier delaminations, corrosion, chloride, moisture penetration. So really understanding that it's not just one tool that you need to use to understand the service life of a bridge. There's multiple conditions on a bridge at any one time, and you need to use multiple methods to really understand the condition of that structure. So obviously visual inspection is something we're all familiar with. We all do very, very well out on structures. Identifying, rust staining, efflorescence, moisture penetration, cracking, spalling, exposed steel. These are the kind of things that we're out there looking for in a visual inspection and are very critical in understanding the condition. In addition, typically we are doing Chaindrag operations, which identifies late-stage, large, near-surface delamination. So that's important to understand. While Chaindrag is extremely effective at finding these and quick, is that the delamination that you find is very late stage. So there is other incipient deterioration occurring beyond what you can find with Chaindrag. Because when you chain over these spots, you're hearing it in the audible it has to be in the audible range for you to hear it. So that noise that you've created is effectively the vibration of the delam based on the chain. And it has to be kind of large and near surface for you to be able to hear that. And so very effective method, but understanding its limitations are important. So how do we use non-destructive testing to kind of supplement those standard tried and true methods? Ground penetrating radar is a very effective method. It's an electromagnetic evaluation of concrete. The nice thing is that the electrical properties of steel and concrete are extremely different, so that steel shows up in in a GPR scan very, very well. So here we have a GPR scan and we see the nice bright white hyperbolas. Those are the steel reinforcement bars. So with GPR, we can identify the reinforcement layout, location of any other embedded metals. We can identify the cover depth of that steel. And we can also do a qualitative condition assessment of the reinforced concrete. We can, chlorides, moisture, and concrete deterioration attenuate GPR signal. So here we have that GPR signal, these nice bright white hyperbolas of the steel. And this is just a white, black, and gray scale representation of the GPR amplitudes. So white is a very positive amplitude, black is a very negative amplitude, and gray is 0. So we see that the white is starting to fade in these reinforcement bars. That's just an indication that the signal amplitude is decreasing. So what will attenuate that signal? Well, it could be potentially chlorides, moisture, or other kind of deterioration. So for cover depth with GPR, service life analysis is probably the most important thing. So cover depth really provides a lot of information about your service life of your structure, and GPR can provide a lot of information about that. So here is a GPR survey of a bridge deck, and we can identify what the cover depth is of every single transverse and longitudinal bar at based on our grid spacing. And we can see here on this bridge that we have an area that's very low cover, that between 1.2 and 1.5 inches of cover depth. So this area is potentially more susceptible to chloride exposure than the rest of the deck. And so that's something we want to take a note of and potentially make corrective action for. This here is the diffusion equation for chlorides. So at some depth x and at some time t, based on the surface concentration and the diffusion coefficient in time. Well, if we rearrange all this for time, we see that depth is exponential. So the larger cover depth you have, it has an exponential impact on the time it takes for the chlorides to reach your steel. So cover depth is probably the most important thing with regards to service life. If we have good concrete, but we don't have good cover, that concrete's doing very little for you. So good quality cover is your first line of defense in the service life. And so using cover depth from the GPR and chloride concentration, we can use these inputs to do a service life analysis and calculate, well, how long will it take for your chlorides to reach your steel? How much of your deck is exposed to potentially over threshold concentrations, and how that concentration will increase over time. And effectively, that's just what these two plots are showing. Just showing a curve. This is at the depth of steel. So we have an average cover depth based on the GPR data, and then plus or minus a standard deviation. So this is where most of our reinforcing steel is on this bridge deck, between 2 and 3.5 inches of cover. And we can see that at time 0, at the day we surveyed the bridge, about 40% of the locations have a chloride concentration above threshold. So effectively, based on coring and GPR, we said, okay, based on the data on this bridge deck, about 40% of your bridge deck has a chloride concentration above threshold. And then using the age of the bridge and the cover of the rest of the deck, we're able to project out using diffusion coefficients how that percentage increases over time. So in another 20 years, you're going to be up to 70% of the deck is potentially at risk for corrosion activity. And then, at 80 years, you're going to be at 90%. So using that information, we can make long-term service life projections and rehabilitation strategies for that bridge deck based on chloride concentrations from cores and GPR data. Cracking has a big effect on bridge deck service life. I showed these nice kind of diffusion curves that are, nice sound concrete. That's how chlorides diffuse into concrete. But when you have a crack, that provides a direct pathway for chlorides to get to your steel. So, now that kind of throws out all the diffusion coefficient and service life modeling, because now you have a direct pathway for chlorides to attack that steel. And there's many causes of concrete cracking in bridge decks: concrete shrinkage due to curing, mechanical stress, improper concrete strength, under-reinforced, ASR, freeze-thaw damage. So all these things can affect your bridge deck service life. Looking at the GPR amplitude analysis, one thing I always like to kind of stress is GPR to amplitude analysis is not a delamination survey. So anyone who says, I'm going to give you a delamination survey with a GPR is not really being completely truthful in that statement. Yes, delaminations affect the amplitude analysis. However, I can't tell you if this area of a signal attenuation, is that a delamination, or is that just near the drainage path and I'm getting a lot of moisture and chlorides there? Now, granted, a lot of moisture and chlorides in a location will potentially lead to a delamination, but at time 0, I don't know that that is exactly a delamination today. So, here is a plot of a bridge deck, and we can see, looking at the attenuation, so this is the plot of the amplitude of the rebar reflection, and we can see that there's attenuation along the deck joint here and along a drainage path here. So it's very common to see where areas of moisture pooling that we have a lot more damage on bridge decks, a lot more chlorides there. But I can't tell you if this is just a lot of moisture and chlorides or if this is a delamination. There's no way to tell the difference between those two signals. However, if we look at GPR overlaid with Chaindrag, there is a lot of similar information, and that's probably why most people think that GPR can identify a delamination. Is the yellow indicates areas on this bridge deck where the attenuation is high, and then the orange is where the Chaindrag survey found deterioration in a spall. And you can see that there's a lot of areas of delamination surrounded by yellow, and you can kind of see where the progression of, okay, yes, they agreed on a deterioration mechanism there, but also GPR is finding more areas than just the delams. It's also finding potentially where corrosion and cracking is occurring outside of that. So you're getting a lot more information and a lot higher level assessment. So in combination, this is a really good assessment of okay, here's where my deterioration is, and here's potentially where that deterioration is going to grow in the next 5-10 years. Another method that we use a lot on bridge decks is half-cell corrosion potential testing. Effectively, we have a reference electrode that's a copper sulfate reference, and we measure the potential difference between that and the embedded reinforcement. And using that, we can identify if corrosion is active at a location. So here's a bridge deck in Washington, D.C. that I did. And here we were doing half-cell potential survey on certain spans and certain lanes through the bridge. It was rather large, so we were doing a sampling. And we can see here that we have a 90% probability of active corrosion based on potential is the kind of the hotter colors. And we can see down the center of the bridge, we have very hot colors down the center. And then kind of along the parapet walls. Again, drainage paths tend to be more deteriorated, so we tend to see higher potentials along drainage paths. But, well, why is this center piece really, really active with regards to corrosion? Well, here's an image of the bridge, and I've kind of highlighted that center patch, and what that is actually a closure pore on the deck. So this deck was cast on the right, the left, and then there was a closure pore in the middle. And there is a construction joint at that closure pore on either side. And that construction joint was allowing a lot of chlorides and moisture to get down to the steel directly. So there was a lot of active corrosion around this construction joint due to access of chlorides and moisture. And so again, we can kind of take a look at how Chaindrag and another technology relate to each other. This in particular is looking at Chaindrag versus corrosion potential. Corrosion potential is telling you where active corrosion is. Chaindrag is where the delamination is. So in combination, they can kind of give you information of not only where damage is today, but where's that damage growing in the next few years. And you can see, okay, we have a delamination here, but we see corrosion is active around these delaminations. And we can kind of project out, okay, if you just go out and chip and patch this area and you don't address the yellow, you're going to have to come back in 2 years to do that next. So maybe is it economically worthwhile to address those yellow areas now and save your maintenance budget in the future? So those are the kind of things that a combination of methods can provide. A lot of times bridge decks use epoxy-coated reinforcement. This, in most cases, can isolate the reinforcement, but there are instances where that's not true. Electrical continuity of the steel is extremely important for half-cell potential testing. So what do we do when we have epoxy-coated reinforcement? Well, we can measure the concrete resistivity, and that can give us an indication as to the corrosive environment provided around the steel. So electrical resistivity of the concrete tells us what the corrosive environment of the concrete is. Now, we're not really understanding is corrosion active on the bar or not, but if the environment around the steel is conducive to corrosion, then there's a probable chance that corrosion will be active. So corrosion, half-cell potential, and electrical resistivity in a chloride exposure environment tend to show very similar information. And so here we have a resistivity survey of a bridge deck, and you can see typically when you're below 40 kiloohm centimeters, that is an environment conducive to corrosion activity. That number, some people say 30, some people say 50, but it depends. Not every, it's not an exact threshold. But you can see there's areas of active potential corrosivity environments here, and the probability of active corrosion when you have a resistivity less than 10 is pretty high. So we can take that information and actually overlay it. So we did half-cell potential survey and resistivity survey on the same bridge deck, and you can kind of see they're extremely similar results. It's not a one-for-one at any means, but you can see that the information is overlaid quite significantly. So you have this kind of darker red, that's where the both surveys indicate potential corrosion activity, and the blue is just where resistivity says, and then the kind of orangey is where just half cell. So there's over almost 80% agreement in the data. So if you have epoxy-coated reinforcement on a bridge deck in a chloride environment, resistivity can provide a quick means to assess the potential risk for corrosion, but understand that it's not going to tell you if exactly corrosion is active or not. And it has to be kind of in a chloride moisture environment because resistivity is really going to be determining our chloride ions and moisture in that concrete. Another technology that we use a lot on bridge decks is impact echo. Impact echo effectively can identify the thickness of a slab, but defects will affect the apparent thickness of that measurement. So if you're not familiar, impact echo is we make an impact on a slab, it creates a stress wave that resonates at a certain frequency. That frequency is based on the velocity of a stress wave in concrete and the thickness of that bouncing. So the thickness is the slab thickness. Effectively, the velocity of the stress wave is almost a constant. We know what about it's going to be. And so that frequency that it resonates at will be related to the thickness. If we have a delamination, then that resonant frequency will have, there would be a higher frequency based on that delamination. And that as that delamination grows, that frequency will change and be associated with that thickness. So we can effectively identify where early stage deterioration is in a slab. So here we can do impact echo testing on a bridge. And we can identify not only where the Chaindrag information, is in agreement with impact, but then beyond that. One of the big problems with DOTs is you do a Chaindrag, and then when you go out and do the chip and patch, those areas tend to grow. And that's because there's much smaller delaminations that the sounder can't hear because it's outside the audible range. So impact echo can identify with greater accuracy the extent of those micro cracking and really get a better idea of quantity on that chip and patch. So here's a bridge deck, and they were able to more accurately identify where those patches needed to be. And this is a rolling impact echo device. So there's an impactor on that wheel. There's 3 sensors this way that measure the impact echo device and also surface wave velocity. So how long that surface wave takes to go from here to here to here will tell us a lot about the velocity of the signal. And you can't see it in this image, but there's also a trailing sensor. So we have impact echo data at that location, so we know the thickness of the slab, if there's any delaminations, and then the shear wave velocity in both directions. Another thing that we use this for in bridge evaluations or just bridge evaluations is post-tension inspection. Paul Fisk talked about this yesterday, and I'll just kind of touch on it. But if you have grouted post-tensioning in your deck or webs or anything, those voids can change the apparent thickness of the slab. And so we can find with impact echo if there's voids in the post-tensioning. And obviously voids cause corrosion and deterioration and failing of post-tensioning, which is a huge problem. And so we did this on a bridge actually on a bridge span in Victoria, British Columbia. It was a pedestrian overpass with 4 PT tendons. The contract inspector noted that the contractor may have made a mistake during grouting. So we went and did impact echo on the 4 tendons and found that the first tendon he just wasn't prepared right, and he had to stop in mid-operation, and then he tried to grout in from the anchorages, and he had 2 20-foot voids on center. And so we were able to find those with impact echo, and here's what it looked like. So, and kind of lastly with the impact echo is the pulse velocity, that shear wave propagation that I was mentioning. So when we make the impact, we have that primary wave and also a shear wave, and we use 4 sensors. So the first 2 are identifying that impact echo frequency, that thickness of the slab, but the horizontal, these last 2 sensors, since we know how the distance between these 4 sensors and how long it takes the wave to get from here to here, we can tell the shear wave velocity. And with that information, we can understand if there's micro cracking or subparallel cracking or things of that nature in the concrete, and that affects the compressive strength of the core. So effectively, with pulse velocity, the shear wave velocity is directly related to the compressive strength of the in-situ concrete. So we can go through a concrete slab, a deck, and identify the in-situ concrete compressive strength and areas where there's obviously a reduction in concrete compressive strength that could be due to cracking, or it could be due, maybe there was a different truck that got poured in this section and that concrete was not up to spec. But so here's a bridge deck where looking at the institute compressive strength based on the shear wave velocity, and you can see, you have up around 5,000 psi here, and then in this range you're down in 3,000, 2,000 psi, which is much different than the rest of the deck. So what happened here versus up there? So those are some things that you can use to identify the condition of your deck.
Quick question on the impact echo. Can that be done in lanes adjacent to traffic, or do you have to have all the traffic off a bridge deck?
The traffic doesn't affect impact echo because the frequency that it's running at and the frequency that the cars are creating aren't anywhere near each other, so it won't have any effect. Yeah.
Has anything been done with the? You're using the chloride threshold that's been used for years. What about the new type rebars that are being used? Has there been any research done on how that affects?
Yeah, that's a very good question. There are people who are working on those numbers. There's all sorts of new, like stainless steels, MMFX, galvanized stainless steel clad bars that are being used in bridge decks these days. I personally am not working on that information, on that research, but I know several people, Virginia Transportation Research Council, Florida Materials Office, they're all working to understand those better at many DOTs around the country. So there's a lot of research going into that. I don't know, where that's at right now, but they're still working on it.
Where in the life cycle of the bridge are you doing these tests? Is it when you're doing your maintenance and preservation work? And obviously you need, or I'm assuming they have to be bare deck, so we're a state that has mostly asphalt overlays, so I'm just wondering about the timing of all these other kinds of tests.
Some of the tests, yes, are restricted by overlays, but some are not. So like GPR can be used without an overlay. Coring obviously can be used without. Half cell is not limited, is limited by overlay, so you have to do it. Sometimes we can do it on the soffit or things like that. As far as timing when we do this in the life cycle, it's kind of dictated a lot by the states. Some states are more proactive than others. Some, okay, I think I have an issue and I need to look at that. Or they're making asset management decisions. So I'd say it's across the gamut of when they're trying to do this. I think with regards to budget and money, obviously the sooner you try and do something like this to assess the deterioration and deal with it, the better. But obviously everyone's trying to play catch up with their inventory, so you don't always have that luxury. So I'd say it's, it kind of depends on where the bridge is. If it's an important structure, they're obviously trying to do this a little bit more early in the stage. If it's a less important structure, then, we're getting there later stage. So, it kind of depends on the owner.
And we also struggle with, we do these surveys, but then the actual programming, takes a while to coordinate with the roadway. And when the metro, we try to, like the other contractor said, we try to bundle projects and get them on a common time scale so that you're impacting traffic one time. Mm-hmm. So I'm not sure how we assess damage tolerance or the time rate from, what can your expectations do if you do a spot survey, and how long do you have in a given chloride environment? Do you have any data on that? And then I guess related is Michigan and other states do polymer overlays, and sometimes the chloride level doesn't matter. They figure if you cut off the moisture, you're much better off. But I'm wondering if there's a chloride threshold you shouldn't do a polymer.
So your first question was, okay, so two parts there.
The first question was, is there a curve for deterioration of rebar once the chloride threshold has been met?
Right. So there is a lot of work on that. So part of my research was looking at, when I was at my PhD, some of this is from that as well, but kind of looking at if you do a couple of methods, for instance, like you do Chaindrag, okay, yes, that's the DLAM today, but we all know by the time you get the bid out and everything going, that's going to have grown. So what do you do to kind of help better assess where it's going to be? So looking at things like half cell potential can potentially better assume that, okay, if you're going to be able to get this repaired in 5 years, half cell is really the active corrosion really tell you where that delamination and corrosion is going in the next few years. So some of those technologies can really identify, can be used to project out a few years early, and chlorides and stuff like that. So a lot of my work was we with LTBP, we were looking at a couple of bridges several times every year and kind of looking at how that damage progressed. And so there's a lot of different people, LTBP included, doing that kind of work. And so some of those kind of looking at the electrochemical reaction of the concrete can kind of help you better assess where that's going. And so you have a more refined quantity knowing that you're not going to be able to get to the repairs right away. And then your second question was about polymer modified overlays and then the chloride content.
Yeah, like epoxy overlays or
Right.
impermeable overlays.
So it all really kind of depends on the steel bar, right? I mean, you're saying that you're probably limiting the oxygen, but a lot of times what I end up seeing is we have ideas and plans that are to say, hey, I'm not going to be able to prevent chloride ingress, but I'm going to be able to limit, potential oxygen or limit potential moisture. Unfortunately, sometimes we get cracks. We did other things that involved in that. So any time of oxygen starvation deck treatments tend to not always starve out as much oxygen as we'd like to think. So I would say, I haven't done a lot of research in that area, but I would say you're probably, if you have bare steel decks, you're probably still at the same threshold. Your corrosion may not be as widespread, though. It might be more localized. So, even though you are kind of depriving some oxygen, so it's not going to be as prolific, it's probably not stopping corrosion based on that threshold. I'd say the threshold's more still related to the pH content and the alkalinity and the steel you're using, but that starvation may be just affecting globality of the corrosion.
With regards to how do we know the damage is going to grow with time, there are actually a couple of service life models available. If you know the distribution of chlorides in your concrete, if you know the cover distribution, and if you know the amount of damage you have, you can mathematically model, and they have been actually verified on decks. So with those three pieces of information, you can project in the next 2 years, 5 years, 50 years, how the damage is going to grow on that particular reinforced concrete element. And with regards to the second question, how, when you put a polymer overlay or anything like that on top, because it impacts the diffusion of moisture and oxygen in it, some of the research we did in the early 1980s, we found that you don't stop corrosion, but you actually lock in the corrosion rate. So the corrosion rate does not increase anymore with time because you've stopped the transportation of some of the elements.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.